So, now as I said that we would look into, so this result was about circuits. Okay. So, we showed lower bound on the size of most circuits computing a Boolean function. Now, we will try to give a similar lower bound for Boolean formula as well. So, lower bound on the size of a formula computing a Boolean function. Okay. So, what is the difference between a circuit and a formula? So, formula is a tree. Yeah, so for a circuit, the out degree of a gate, the fan out can be more than 1. For a formula, it is at most 1. Okay. In other words, the DAG is a tree over here. Okay. Okay. So, theorem. So, this theorem is by Riordan and Shannon. So, let delta be a quantity smaller than 1. Most Boolean formulae require, or sorry, most Boolean functions require okay, let me just rewrite this. For most Boolean function f L B2 of f is at least as large as delta 2 to the power n by log n. Okay. And here what we will do is, I will just make a small modification to this theorem. We will not look at the total number of gates, we will look at the star size of the formula. Okay. So, remember what we meant by star size. So, star size is basically counting the number of OR and AND gates. Okay. We will not count the number of NOT gates, and we will actually consider this yeah, we will not count the number of NOT gates. Okay. So, I will refer to this as L star. For most Boolean functions f, the star size L star B2f is at least this quantity. Okay. So, let us just try to understand the difference between this theorem and the previous theorem. On the previous theorem, so which of these two quantities is larger? So, previous theorem we had 2 to the power n by n, here we have 2 to the power n by log n. Okay. So, this is a larger quantity. So, essentially this is a more, so this is a better lower bound. Okay. So, what we are saying is that the formula would have an even larger quantity, which is what we expect. Okay, because the formula is a more restricted version of computation, it is a more restricted computational model. Therefore, we expect that the size of the formula to be larger, which is what we get from this theory. Okay. So, how do we get this denominator of log n instead of n? No, I use this thing L, na. So, I gave the definition earlier. So, look at the definition that I gave, that C omega is the smallest size circuit computing a formula, and L omega is basically the smallest size formula. Okay. Yeah, I can write it as well, the star size of a formula for the function comma L star B2 of f. Okay, actually I have a name for the function, so let me use the name for the formula computing f is this much. Okay. Okay. So, now the question is how do we count the number of Boolean formula. Okay. So, before we get into how we count the number of Boolean formula, let me just talk about a notation for representing Boolean formula. Okay. So, how can we so what is a Boolean formula? Pictorially a Boolean formula is a tree. Okay. How can we represent, and we are looking at binary trees over here. So, it is a binary tree. How can we represent a binary tree? So, binary tree can be represented in many ways. So, there is in order notation, there is postfix notation, there is prefix notation. So, we will look at the postfix notation, and I will tell you very soon why we consider postfix notation. So, what is postfix notation? Let me quickly talk about it. The postfix notation for a Boolean formula has the operands before the operator. Okay, so this is actually a very crude definition, a very informal definition, but this would be enough for us, because let us look at it with some examples, okay, couple of examples. So, suppose I have a Boolean formula x or y and then and z. Okay. So, what would be the postfix notation for this Boolean formula? So, any guesses? So, it would be, I want to compute this first. Okay. So, it would be x, y or, and then to the result of this I am conjugating z. So, it will be z and. Okay. Now, for the same order, if I have x or y and z, where y and z is computed first, what would be the postfix notation? Huh? No, it would be again x, y, z and or. Okay. So, I would keep on looking at the operands until I get an operator. So, the moment I get an operator, I look at the previous two operand, which is y z. So, I do y z and I get that result, and then with that result I do or with x. Okay. So, the point is that if you look at the relative order of the variables, they remain the same, which is the same case as over here. But what is the advantage of postfix notation? Huh? It eliminates the requirement of brackets or parentheses. Okay. You do not need. So, once you give a postfix notation, you do not need to put parentheses anymore if you write the notation carefully. Okay. So, this is why we use postfix notation. So, postfix notation eliminates the need for parenthesis. Okay. So, this is the infix notation or the standard notation that we use. Here, if we do not specify the parenthesis, it could mean either of the two precedences. Okay. So, either this can get precedence or this can get precedence, unless you have a specified order of precedences, but here you do not need to specify that. Okay. And this therefore, parsing is unambiguous. Okay. Okay. So, why are we looking at postfix notation? The reason why we are looking at postfix notation is because what we will count is that for a Boolean formula of a fixed size, how many different postfix notations are there. So, consider a Boolean formula of size S. Okay. Now, how many ways can I write this string? So, first of all, how many characters will be present in this string? And assume here that there are no NOT gates. Okay. So, each gate has a fan in 2, let us assume that. The reason why we assume this is because we are only computing the star size. Okay. That is why. How many or before I even get into the number of characters in this string, think of a tree which has S internal nodes and some n leaf nodes. What would be the size of this tree? So, that tree size will be n plus s minus 1, right. So, now consider this formula. Okay. What would be the number of characters in this formula? So, actually it is not n plus s minus 1 over here. Why is it not n plus s minus 1? Yes. So, the same variable can be repeated. Okay. So, when you say n plus s minus 1, you are assuming that for every input variable you have a single gate, but that need not be the case, because it is a tree. The same variable can go to different, I mean if the same variable has to go to different gates, you need different copies of that variable. Okay. So, the total number of gates would be yes, how many? S number of gates, but what is the total number of nodes in that tree? 2s plus 1, exactly. Okay. So, any binary tree with s internal nodes has a total of 2s plus 1 many nodes, correct. Okay. So, therefore, the length of the string representing the formula is 2s plus 1. Okay. Now, let us look at a string which has length 2s plus 1 and let us count the total number of possibilities for that string. So, first of all, these gates can be, how many gates are there? S many gates. Okay. And these S gates can be in any of the S positions. Okay. So, there are total 2s plus 1 many positions. So, it can be in any of these S positions. So, I have a total possibility of 2s plus 1 choose S many possibilities. So, this is fixing the gate positions. Now, each of those gates can have how many different possibilities? 16 different possibilities. Okay, I mean not as, it does not matter, it is some constant. So, let us say 16. So, there are this many possibilities for the gate. Each gate can have 16 possibilities. So, it is 16 times S, and each variable can have how many possibility? N possibilities. And how many such variable nodes are there? S plus 1 many variable nodes. So, each of those S plus 1 variable nodes can have n possibilities. So, n to the power S plus 1. Okay. So, this is the number of possible sequences representing a Boolean formula of size S over n variables. Okay. So, we are doing nothing very fancy over here, just counting the number of such sequences. Once again, many of these sequences even need not correspond to a formula. I mean, you can have sequences, I mean, for example, if I have something like a sequence which begins with, let us say, or x y, that does not even mean anything in the postfix notation. We ignore such things. I mean, it is okay, we are just interested in a upper bound. So, now let us try to once again estimate this quantity. So, this again we can use Stirling's approximation over here. So, this is like 2s plus 1 whole factorial divided by s factorial times s plus 1 factorial. So, we use Stirling's approximation over here, and we can simplify this to so this quantity 2s plus 1 choose s is upper bounded by 4 to the power s by Stirling's approximation. Okay. So, now what we have is 2s plus 1 choose s times 16 to the power s, n to the power s plus 1 is at most 4 into 16 is 64. So, this would be 64 to the power s times n to the power s plus 1, and I can write this as some constant c times c to the power s times n to the power s plus 1. Okay. Now, we will try to see what this quantity becomes. Okay. So, we set S to be so we will set S to be delta 2 to the power n by log n, delta 2 to the power n by log n. Now, let us try to see what that becomes. So, therefore, c to the power s times n to the power s plus 1 is equal to c to the power delta 2 to the power n by log n times n to the power delta 2 to the power n by log n times n. Okay, so, that extra n is coming because of this plus 1 over here. Now, we will do a change of basis, and we will write this as a power of 2 over here. So, I can write this as 2 to the power delta log C whole to the power n by log n, and this will become 2 to the power delta log n to the power n by log n. Okay, so let me just check whether this is the correct thing. Okay, so okay, so maybe I might be making a mistake here. So let's try to do this a little more carefully. Sorry, so this was n to the power this times n, right? So we can write this as C raised to the power 2 raised to the power n whole delta by log n. Okay. Yeah, and this I can write as n raised to the power 2 raised to the power n delta by log n. Now I want to write both these as base 2. So what would that be? So this would be 2 to the power huh? 2 to the power? Yeah. So 2 to the power n times log C. Let's just verify this. So if I take log yeah, exactly. And I do the same thing over here as well. So this would be 2 to the power into log n delta by log n times n. Okay. So this log n and log n cancels out. So what we have is 2 to the power n whole to the power delta, and here we have two to the power n log C by log n times delta 2 to the power n times delta times n over here. So this is what? One plus log C by log n whole to the power of delta times n, right? So once again, log C by log n is asymptotic, I mean as n tends to infinity, this quantity tends to 0. So, this is very close to 1. So, therefore, this entire quantity is asymptotically smaller than 2 to the power 2 to the power n. Huh? Delta, we can take delta to be any constant less than 1. Okay. So, since delta is less than 1, as I mean no, if delta is 1, this will yeah, then it won't approach, I mean it won't be asymptotically smaller than 2 to the power 2 to the power n. Na? So, if you take delta to be 1, then you have 2 to the power 2 to the power n times 1 plus log c by log n, which can be bigger than 2 to the power 2 to the power n, right, because this quantity is still, I mean this quantity is still greater than 1. So, this quantity is greater than 0, right. So, only when I take delta to be a constant less than 1, this drops down. Therefore, for most Boolean functions, we require formula of size more than 2 to the power n by log n. Okay. Well, for any delta that is less than 1.